Okay, thanks for the invitation and the introduction. So today I'm going to talk about some joint work with Mingyun Xie. So the main result of the talk today is the joint work, actually still in progress with Mingyun Xie. Okay, so I'm going to start with some motivation. So I will first fix an alt prime P, and then I will fix a embedding of Q bar into QP bar and the C complex numbers. And I take a finite extension of QP and denote by O inside F the ring of integers. And I will take the two capital modular forms, F and G. I was assume that the Fourier coefficients are algebraic numbers and actually lies inside the ring O. And associated to F and G, I have two Heck eigensystems. I denote by lambda F, lambda G. Goes from the Heck algebras to O. And also there will be the two Galois representations. And I will add an assumption that their central character, the product of the central character is trivial. And then I consider the Yoshida lifts for these two Heck eigensystems or the two Galois representations. So the Yoshida lifts. So it's the Heck eigensystem for a GSP4. So for the Heck algebra of GSP4, corresponding to the Galois representation, which is essentially the direct sum of the rho F and rho G. Oh, so this is the Yoshida lift of uh, the two Heck eigensystems. And then from this, we know that Galois representation is actually decomposable. So then what we want to consider is the congruences between this Heck eigensystem, lambda Fg, to other Heck eigensystems for other forms on the GSP4. So we have the following picture. So we have the Heck algebra of GSP4. So the Heck algebra acting on the modular forms of genus 2, and I can tensor it with this is the integral Heck algebra, then I tensor it with the F, the, and then it can decompose into two parts. One factor is F, and the other is then there's another factor. So the first factor corresponds to the eigensystem, so lambda F comma G, and I will denote the projection to the second factor by P2, the second projection. And we consider the so-called congruence ideal, which is defined as, so I denote it by C parenthesis F comma G, to be the image under lambda Fg of the kernel of P2. So this is going to be an ideal inside O. So this is the congruence ideal. So this is kind of measures how much congruences there is for the Hegel system of the Yoshida leaves and other Hegel systems. And another way to think of it is kind of is somehow it measures the projection to the first factor. So from if I consider, so let me write this way. So if I consider, so there is an element after tensoring with F, there is an element here. I call it 1 lambda FG. So this is kind of the projecting to the system of lambda FG. So goes to 1 comma 0. So this congruence ideal also somehow measures how far this projection from being integral. So we know that if there are a lot of congruences, then this projection is not going to be integral. So kind of. And so why kind of we're interested in this congruence ideal? So the reason is somehow it's because by the Ribes lemma we know that the congruence. So if we have another stable form which has a congruence with that is Yoshida leaves, that means there is going to be an irreducible Galois representation that is congruent to this reducible Galois representation. And the Ribes lemma tells us this is going to give us a lower bound for the Selmer group attached to the tensor product of rho f and rho g. And also, we kind of know and we have an expectation of what this congruence ideal should be. Actually, this should be the expectation is that this should be equal to a properly normalized L value at 1 for the Rankin-Selberg L function of L, F and G. So I will put a superscript ALG to denote the properly normalized L values, meaning dividing by the correct period and then multiplying divided by the properly integrally normalized period. Okay. So this is kind of the expectation. So that means the goal is kind of we want to study this congruence ideal and show its relation with this L value, and then in the end we can deduce the a lower bound of the Selmer group in terms of this L value. Okay, so that's kind of a motivation, and next, I'm gonna quickly say a strategy for kind of a general strategy for studying this type of congruence. So I will write. So this is a strategy following Hida and Thielemann, where they study the congruences with CM forms to study the Mann conjecture for CM characters. So now I would need to kind of before I view this Yoshida lift as just kind of simply lift the hack ecosystems, and now I need to say a bit about kind of Yoshida lift as an actual Ziegel modular form through the theta lifts. So I'm gonna assume that. So because the reason because I want to kind of reduce the study of kind of the congruence between the Hegel systems back to the congruence between the among the Ziegel modular forms. So we assume there exists a quaternion algebra, definite at infinity, and such that both f and g admit a Jagiellonian transfer to this quaternion algebra. So I denote it as FD and GD. And then we know that actually the two copies, so then this is going to be a form on two copies of D cross. And we know that D cross kind of is related to the O4. So we have D cross times D cross quotient by a copy of GL1 is actually isomorphic to GSO4. And so this orthogonal, there is a kind of a symmetric pairing on the quaternion algebra. This GSO4 is just orthogonal group for the symmetric space D. And then we have the theta lift to GSP4. So I have my pair of forms on the quaternion algebra, and then it goes to a theta lift. So after choosing a Schwartz function, so this is going to be a automorphic form on GSP4, and we can make the choice at the Archimedean place so that this is actually an holomorphic modular form on GSP4. And then what we can do is the following. So we take a cuspidal holomorphic Lego modular form, like denoted by capital F on GSP4. So with periodically integral Fourier coefficients. And then what we consider is the following. So as we said, the congruence ideal somehow measures how far this projection is actually not integral. So what we can do is, okay, so we take an integral form f and then we apply this projection to it and see what is the denominator. So we consider. And we know that this projection, somehow we can reinterpret it as somehow we take the Peterson inner product between the Yoshida lifts, the automorphic form with this form F. So now if we look at the congruence ideal, so what we know is that if I take any alpha inside the kernel of the projection to the second factor, then we know that alpha is actually equal to alpha times the projection. And then this is equal to the value of alpha under the lambda fg and then times the projection. And because alpha is taken from the kernel of the second factor, actually, which is it's taken from the integral Hacker algebra. So therefore, we know that alpha time acting on f should be integral. And so therefore, this tells me that uh, lambda f comma g alpha then times this one lambda fg acting on f should be an integral Ziegler modular form. So that means if I multiply the lambda f comma g alpha to this whole thing here, I should get an something inside the ring of integers. So that means the denominator of this one lambda alpha, one lambda fg acting on f should divide. So every element in kernel P2 mapped by lambda fg. And so that means that divides actually every element by the definition. So divide every element inside the congruence ideal. And so uh, that means what we want is kind of to study the denominator of this expression here. And what we want to do is actually make the proper choices such that this term is going to be a Ziegler modular form, which is kind of periodically primitive, meaning that it have a Fourier coefficient, which is a periodic unit. And also we want to arrange this Peterson inner product somehow give us a periodic unit. And then the denominator of this whole thing is going to boils down to this denominator here, the Peterson norm of the theta ellipse. And for this Peterson norm, actually, we know there is the Rayleigh's inner product to tell us it's actually related to the L value of the Rankin-Sauerbrei function for f and g at 1. Okay, so what we want to do is the following. So with the specific choice of our Schwarz function for doing the theta lift, and so we want to do so we need, so first we want to relate the Peterson norm on the denominator to rank values of Rankin-Sauerbrei function. This is kind of expected what should be somehow the congruence ideal. And so for this, that means we need to kind of explicitly compute the local data integrals in Rayleigh's inner product formula. And so that is about this term. And then we also need this term on the numerator. And so that means we need a choose a suitable F such that somehow we can show that this Peter's inner product. So probably after appropriate suitable normalization should be a p-adic unit, and the way it's kind of the way to choose this F, that somehow is meaning that we need some good F, so that certain type of F, so we have a kind of we can interpret this as a we have the automorphic integral formulas to interpret this as certain L values. To certain L values for which we hope that we could have some multi non-vanishing results about those L values in order to show this is a unit. And the last step is also to show this part is actually a primitive zygomodular form. We show this is integral and as a Fourier coefficients, which is a p-adic unit. So again, for this step is again we need to choose a suitable automorphic period to reduce studying its Fourier coefficients to studying some certain L values for which we have multi non-vanishing results. Okay, so these are kind of the three ingredients that we want to in order to get a bond of the congruence ideal in terms of the L values. Okay, so any questions so far? Okay,
So sorry, just a quick question. When you're talking about the
mhm.
Peterson inner product, do you normalize it some way so that it's in Q bar?
Right, actually we do need to kind of normalize it, and also it's kind of yeah, later after we study kind of like when we study like p-adic congruences, when we choose level which is not spherical at p, then actually we also need to modify this Peter-Schindler product a little bit to kind of in order um to put in to be suitable for the setting for studying the congruences.
Okay, thanks.
Okay, so there are some previous work on this doing all these three aspects. So first is under certain conditions of FRG, and so for the previous report, mostly they just assume it's spherical at P, and all other primes is either spherical or ramified or Sternberg. So for the first part, to compute the Peterson norm of the theta lifts in term via the Rayleigh's inner product formula. There is a previous work by the Barker and Domigan and Schroeder Pillard, and also Shi and Namikawa. Is for the first computation, and for the second computation, which is about choosing a suitable F so that we can consider this Peterson inner product. So the previously people what they use for F is what they use is kind of the Ziegel-Eisenstein series on GSP8. And then they restrict it back to GSP4 times GSP4. Then it's not gonna be an eigenform, so therefore you can hope that use it to Peter pairing with the theta lifts gonna give you some information about the congruence ideal. And so actually this case is gonna be two copies of F. And when we consider this Peters inner product, and then this is a, okay, sorry, so this is not, okay, so I got, okay, so it's a two copies of these theta lifts with the F, okay. And for this one, actually, what we can quickly recognize is that this is actually a doubling that integral because we have Ziegler-Eisenstein series on the GSP8 with the size of the group doubled. And we know the Gart and the Rallis, Piatetsky, Shapiro, the doubling method is this one is gonna give us an L value, L function. So if we have the S and so this Ziegler-Eisenstein series are kind of inducing the S and chi times the norm to the S, then it's gonna give us the standard L function on GSP4, which is degree 5 L function. And in this case, because this is Yoshida lifts, it's gonna factorize to a degree 4 L part, which is the Rankin-Selberg L function for F and G, and the degree 1 part, which is the Dirichlet L function. And so this has been done. So this has been done by many people like Shimura and Barker Schmidt and Barker Schultz Pilot. But there is the issue with this one is actually, so this it doesn't completely actually maybe I put a star here. So this doesn't completely address gives what we want. So what we want is this Peterson product should give us a periodic units, but actually for this L function, we don't know good enough multi non-vanishing results to show that actually I can choose S and chi such that this indeed gives us a unit. So in the previous work, when people study this, what they do is to kind of formulate the result as, okay, so if there exists a choice such that this is a unit, then then they can deduce a lower bound of the congruence ideal. So this part is kind of in the previous work is not kind of ideal because we didn't get a value that we indeed have a way to prove it's multi non-vanishing. Sorry, excuse me. Okay, then the third step is to show that this theta lift itself is integral and primitive. And for this, what one can do is to choose the Bessel period to study which is kind of a linear combination of the Fourier coefficients. And the Bessel period, we know that is actually equal to the central L value of F and G twisted by a character of an imaginary quadratic field. So this approach has been studied by GI and also in the paper by Shi and Namikawa. And we know that these two L values actually we do have results for non-vanishing of modulo mod p non-vanishing for these two central L values. So we do have that means we can choose a suitable Kasi such that the properly normalized these two L values are both mod p non-vanishing. So this part is nice. We do have the result. So this is result due to Vassar and Kony-Vassar. Okay, so that's the in the previous work, all the three steps, and also assembling all these three steps, there works to kind of deduce a lower bound for the congruence ideal, and then first further to deduce the Selmer groups for the bound on Selmer groups for F and G. And so this has been done also in the work by Agor Clausing and Barker Domigan, Schwartz Pillard. And also there is a more recent work by Xie and Pavanan, which instead of considering the fixed modular forms F and G, they consider F and G being two Hida families of modular forms. And then they deduce some one divisibility of some kind of Iwasawa-Man conjecture with two variables. Okay, so this is the previous work. And next, I'm gonna say what we want to do in our project. So what we do. Okay, so as discussed before, so I think in the picture, I think the main defect is about the second step. So the choice of the integral legal modular form on GSP4, the choice of F. And so what we want to do is kind of get a better choice. Better choice of F. And also because the work by Xie and Pavanen already did in the setting of the Hida families. So we also want to study the congruence ideal for Hida families, and so therefore, in the end, to combine with their results to deduce a one divisibility in of the Iwasawa-Man conjecture. So we want to study the congruence ideal uh, with F and G. So I've used an underline to denote the Hida families to denote. So with this F and G being Hida families. So to think of Hida families, we can also just think of this as kind of a kind of a periodic analytic family of Hecke systems. So it goes from the Hecke algebra of GL2 into the instead of the ring of integers O, we map it into the lambda, which is the Iwasawa algebra. So these are kind of so-called the Hida families. And then when we specialize, so we put T to certain values and it's gonna recover the Hecke system class corresponding to classical modular forms. So this kind of rough idea was Hida families. And we want to prove the following theorem. So we let F and G be Hida families. of time level gamma not n. So meaning that the Higgs eigensystem A parameterizes comes from modular forms, which is fixed. So for away from P is going to be fixed by gamma not n. And then we suppose we need to put some conditions on these two families. So we suppose that the corresponding, so for the Hida families, we're gonna have the uh, Galois permutations. We assume that they are absolutely irreducible. And then we also assume that this level n is equal to n plus times n minus square. We'll consider the square free level. And also, we want to be able to get Jagiellonian transfer to a quaternion algebra definite at infinity. So we want to assume that cover a minus having all number of prime factors. So we know then we require that for any uh, prime dividing n minus, we want that this f and g are both new at the primes dividing all numbers. Meaning there are kind of Sternberg there. And also for any Q dividing n plus. So at n plus, we can allow either Sternberg or unramified. But if both of them are Sternberg, then we want to require that they have their local sign are the same. So these are the conditions, and then what we deduce is that the congruence ideal actually is contained inside a periodic L function for the f and g, and then times the congruence ideal for f and times the congruence ideal for g. So here this LFG is the so-called two variable Rankin-Selberg periodic L function. So we can view it as an element inside. So two variable meaning it's inside the Iwasawa algebra with two variables, O double bracket T1, T2. And so then if we specialize the values at some values of T1 and T2, it's gonna interpolating the Rank-Selberg L function valued at 1. So this is the result. So if we combine this result with the previously mentioned result by Xie and Pavanen, then we get we deduce that the characteristic ideal of certain Selmer group is contained inside the ideal generated by this two variable Rankin-Selberg PIDL function. Okay. So this is the result. And then next I'm gonna talk about the method. So what goes into the proof here. Okay, so already I kind of already before I already sketched a kind of a general strategy. We just need to fill in the ingredients. And so the one key ingredient is the choice of F, choice of this capital F. And so we're gonna get this new choice. We're gonna use, say, the Eisenstein series. Again, we're gonna use the night again. Use Ziegel Eisenstein series, but this time instead of goes to GSP 8, we consider GU33. So we consider Eisenstein series. We restrict to GSP 4, actually cross GL2, where this Eisenstein series is a Ziegel Eisenstein series on GU33, inducing a Hacker character of an imaginary quadratic field. So I denote it by C. And also, in this case, it's gonna restrict to GSP4 cross GL2. So also we need to choose an auxiliary form on GL2. So we take auxiliary CM form H on GL2. And now we consider the Peterson inner product or the Hack projection of this module, legal modular form, and we know this is almost like a Peterson inner product. Okay, so then what we want to do is, so now we get this, and then we want to show this part. Want to show this part is actually equal to a periodic unit divided by the normalized L the value Rankin-Selberg L value. Okay, so now that's what we need to do. And so that means the choice of this F here as the restriction of the Ziegel module form on GeoC3, of course, is because we have some automorphic integral formula there. And in this case, actually, it's the Furusawa's formula. So what we have, so we want to study this ratio here. We know that this is almost like the product of the Rankin-Selberg L function for f and h and g and h, and then times the Bessel period for the theta lifts, which actually already studied before, and then times a Whittaker period of h. Essentially, here is just the Fourier coefficients of the modular form, CM form, and then divided by the denominator. And this is by the, so we know this is Furusawa's formula. Which is about the, actually Furusawa's formula actually studies L functions for GSP4 cross GL2. And in our case here, because we have a Yoshida lift, so therefore the GSP4 cross GL2 degree 8 function splits into the product of two degree 4 functions, which is the product of the two Rankin-Selberg functions here. And then the next step is the Rayleigh's inner product formula to reduce the numerator to the L value we're interested in actually. So here we know that this is going to be roughly the Rankin-Selberg value at 1 of f and g, and then times the norm of f, the norm of g, and then h. So this is a Rayleigh's inner product formula. And then once we get here, so mostly all the terms we have are L values, which is the normalized term, collect range the periods together. So one can check that if we put S equals 0, and I will have the central L value for F and H, and then again another central L value for G and H, and then I have the Bessel period and the Whittaker period of H. And then I have the normalized part of G, and then this will be the congruence ideal for F, then congruence ideal for G, and then congruence ideal for H. And so then the last expression is going to be very nice because we have the result to handle all the terms here. So what we have is, so for these first two terms here, what we want to be units, we do have the P non-vanishing results here because H is a CM form. So this basically is the function, the f and twisted by a imaginary Hacker character of an imaginary quadratic field, and for that we have P non-vanishing result. So we have result. Then again is by the Basel and the Basel, and a different type of vanishing result by Hida and the Xie. And then this part will be good, and also this part, the second part, as we saw, we already know how to. We also know how to handle this part. Also, we have P non-vanishing result. So therefore, that means we're done. Actually, we once we know that this numerators is a periodic unit, then we know exactly this the denominator is the one on the what we see here, which is kind of gives us the normalized values of fn for this Rankin-Selberg at L function at 1. Okay, so this is kind of the strategy. And once we see the picture here, that we know, okay, so in principle, we will be able to get what we want. So we do have the automorphic integrals and the P non-vanishing results. And so therefore, what we need kind of boils down to carry out the computation to really establish these two equalities here. So that means Okay, so the picture is already here, then the remaining is kind of the computation part, which it can be not so pleasant. So I have three terms here. So then this is the choice of f. We know that in principle it can work. And then the second part will be to establish the relation between A and C. So we know that C is the term, this term is what we can handle, and then the A is the one that's showing up in the strategy for studying the congruence. And so that means need to compute a lot of local data integrals. And so in particular at P and infinity. So at other ramified primes, we can either kind of use some previous results or kind of adding some simplifying conditions. But at P and infinity, that's the place that we have to do all the computation. And so then we started trying to do the computation. So we try to directly carry out the computation. So what we managed to do is the following. So we have three terms. So what we want to do is first Furusawa formula from A to B, and then Rayleigh's inner product from B to C. Okay, so what we managed to do is for the Furusawa formula, we can handle the computation at P for kind of all the forms that is ordinary, that is relevant for us here. But for the Archimedean place, we were only able to handle the scalar weight. So we require the theta lifts to be the scalar weight. And also we want this weight to be equal to the weight of H. So only in this case, computation is not too difficult at the Archimedean place. And we also did the Raleigh's inner product formula. So before the recomputation is for spherical case, and now we are considering the Hida family, so we need to consider more general case when the form is not spherical but kind of the eigenvectors for certain UP operators. And so what we can do is so this type is for Archimedean places are okay, but at P, we require trivial Newton types for F and G, trivial Newton types at P. And so we got these two results, I call it star and star and star. So somehow you can see that these two kind of direct computation, the conditions do not match very well. One is you put restriction on the Archimedean place, the other is you put restriction at place P. So combined, that means you have a lot of restrictions. So that means the conditions for star and the double star are kind of very restrictive. So in particular, if we want to kind of do Hida families and p-adic functions of everything, uh, these two conditions together actually don't give us enough points to deduce the p-adic interpolations or the p-adic functions agree with each other. So in particular, it's not sufficient for showing that if we interpolate A and C into families, into the some periodic analytic uh, functions, it's not enough to deduce they are equal. So where this is A and C are periodic analytic interpolation of A and C. So in general, when we work with kind of these periodic interpolations, periodic families, we know that sometimes we don't need to do the computation for every case because what in the end we get some periodic analytic interpolation, periodic analytic functions. If we know information at enough points, then somehow we can already deduce some equality for the two periodic analytic functions. But unfortunately, this case that's not gonna with these both conditions, it's gonna be not enough points. And so that means we need to come up, either we need to work harder to do more computation, or we need to kind of get some way to bypass this issue. So what we notice here is that actually in the periodic interpolation, if we only put conditions at the Archimedean place, like scalar weight, then that's gonna give us enough points because we allow all kinds of Nibben-typers at P. Or if we only put conditions at P, but we allow all the weights at the Archimedean place, then often it also gives us enough points to deduce two periodic analytic functions are actually the same. So excuse me. And so therefore, in this case, what we want to do is here, actually, then what we realize is that what we need to do is to kind of, because we have these two steps, so that means instead of directly compare A and C, we want to compare A and B in families, and then B and C in families. Then those conditions will be enough. And so therefore it boils down to kind of interpolate this B term here. So what we need is to kind of idea here is to periodically interpolate this B. And so this actually boils down to that means we need to interpolate. Actually, what we need to interpolate is gonna be a Peterson inner product. So what we need to interpolate is to interpolate this Peterson inner product. Or more precisely, the ratio of the Peterson inner product. Okay, so we need to do this, and then you say, okay, so then this from the Rayleigh's inner product, this is the Rankin-Selberg L value, and this is actually the period for that Rankin-Selberg L value. So this whole thing is actually the Rankin-Selberg L value, and we know that we have P as Rankin-Selberg PL function to interpolate it. But actually, this is actually gonna run us into the circular argument because actually the reason we need to consider this is because we are not able to compute enough cases for this Peterson inner product to the Rankin-Selberg L value. So that means actually we need to not use the relation through the Rayleigh's inner product to interpolate this without using the Rayleigh's inner product formula. Related to this L value. We want to consider this exactly because we are not able to compute enough cases for the local data integrals. And so what we really finally realize is that actually what we can do is to interpret this ratio in terms of another kind of ratios of other types of PIDL functions. So what we can do is to, so actually we can interpret it as the ratio of the L function for f and Rankin-Selberg L function, and then times Riemann zeta function, and then divided by the standard L function of the theta lift. Actually, we know that the standard function is a degree 5 PL function, and in the Yoshida lift, the theta lift case, actually it factorized exactly as the Rankin-Selberg function, then times a Riemann zeta function. So actually, as a function, these two are the same. So therefore the ratio of their normalization actually gives us the ratio of the Peterson norm, kind of the ratio of the periods. And luckily we do have all these periodic L functions for all these three terms. So and then use Rankin-Selberg periodic L function by Hida and Kubota Leopold PIDL function for these data values. So L function, and then use the PIDL function for the degree 5 L function on GSP4 for the standard PIDL function for GSP4 and periodic L function, standard PIDL function or PIDL function for SP4, the degree 5 one, which actually I first considered by Barker Schmidt, and also I did it in my thesis. So therefore, combining all this type of three type of PIL functions, somehow we get a periodic interpolation of the period of this one. And so therefore, with this PIL, then we can bypass the computation of many local data computations of local data integrals to get the equality we need. And also through this as a byproduct, we can compute the Archimedean data integrals for the Furusawa's formula for the GSP4 cross GL2 case for the holomorphic discrete series through this kind of periodic method to evaluate the Archimedean data integrals there. Okay, so I guess I'm already over time, so I'm gonna stop here. Thanks for your attention.
Okay, thank you very much for the nice talk.